So first of all, good morning, everyone. Thank you for joining our May IMEDS community call today. This is Christine Yu from the Reagan-Udall Foundation. Before we start, I just want to remind everyone that this group is right now put on mute for the time being to cut back on the background noise, and we will be unmuting everyone at the end for the question and answer period. So for today's presentation, we're happy to have Dr. Vojtech Huser from the NIH Clinical Center with us. He's also a Odyssey collaborator, and he's here to present to us his work titled The Methods and Tools to Evaluate Data Quality and Data Size. Dr. Huser is a user of the IMEDS lab, and his work in the lab has been submitted for publication earlier this year. So for the presentation, you should have received this slide deck in an email yesterday, and you should also be able to see the presentation on your screen. Please do know that this presentation is being recorded, and we will be putting a copy of it on our website after this call. So Dr. Huser, thank you very much for taking the time to present to us today. And with that, I'll now turn the presentation over to you.
Okay. Hello. Hopefully everyone can hear me and see the slide deck. So as I said, I recently actually switched from NIH Clinical Center to the National Library of Medicine, but it's still part of the intramural research program in Bethesda in Maryland. And thank you for coming. Hopefully it'll be interesting. I'm a physician by background and PhD in biomedical informatics. And as you will see from some of the mini studies I'll present, data quality has been of my interest for a while. So this is the short, brief agenda for my talk, and as I transition from one topic to the other, I will present the same agenda and highlight the section I'm in. I'll first focus on some of the three small studies which led me to the main study one, which will be about 60% of the talk. And then I will briefly touch on some extensions inspired by the first study to data quality. And also, maybe some of the previous talks are very clinical in their nature. This is very informatics type of topic where I don't pursue any given clinical question around a drug or a diagnosis or procedure, but it's really focused on an informatics problem of data quality. So it may be slightly different than what you may be used to from some of the other talks. I also, before I start presenting, I want to thank Reagan-Udall Foundation for the FDA and for creating the IMEDS program. I want to say that the virtual machine infrastructure is really excellent. There's a fast Redshift DB engine, so there's a lot to be thankful for, to conversion of data to some common data model, so we don't have to deal with so many different specs. And also allowing multiple analytical tools, which is a huge advantage, for example, compared with the VRDC, Virtual Research Data Center for the CMS. And I would like to thank the Odyssey community members for their input to this work. In fact, the study one is really using someone else's work, and I was only using the tool and comparing the output. So the credit goes a lot to some of the original creators of the tool I will feature. So in terms of prior work, how I came to the problem is when I was working at Intermountain Healthcare, actually a while ago, almost more than 10 years ago, I encountered a problem that I was analyzing Hodgkin lymphoma patients and whether the chemotherapy they went through because of the leukemia destroyed their reproductive function, and if it didn't, they were able to have kids, even because this is a cancer which is highly treatable. And I somehow needed to know whether there was an event of delivery of child, but I also needed to know if there are potentially on a contraception strategy, or some contraception pill or other things. And at that time, the integrated delivery network of Intermountain Healthcare did not have any OBGYN outpatient clinics within their network. They were private. They were outside their system. So I basically had to abandon the study, and this was the first encounter with a data gap which basically prevents going further. So I later, as I mentioned, those mini studies, so the two of the mini studies, I mentioned the reference, and I'm going to describe them later. So my initial question was, how would you evaluate, an IDR stands for Integrated Data Repository. Now we would be going back to the data warehouse. At that time, the Integrated Data Repository, the integrated meant that your genomics data or claims plus healthcare plus health plan, EHR, it's all integrated in one data repository. That's hence the term IDR, Integrated Data Repository. So is your repository better in 2012 versus in 2007, or which one should you use for your study? The first one, at institution A or at institution B, if you have a choice. Within OMOP, I was inspired by these graphs, which at a first glance show you the density of the data and a couple of databases compared, so you don't have to study numerous PDFs to get a good picture of what the study looks like or what the data looks like. So the motivation for pursuing data quality, or I was really I wanted to have like something like an APGAR score for a data warehouse or for a data set. Is it a good data set or not so good data set? And one would basically study whether the data repository is improving, whether it's ideal for a particular research study. It should be on a generic level, not specific to, for example, a heart valve study in pediatric population. And it built on some of the surveys of data repositories run by participating sites within the CTSA grant and those surveys done in those years. And one can be an academic medical center, as I mentioned, with this problem of limited number of outpatient clinics. It could be a large network, integrated delivery network, something like Partners Healthcare, or I would say always the ultimate data set for most research questions is a data set similar to maybe Kaiser Permanente in South California, where there is a health plan component in addition to a very comprehensive delivery network. And another thing to keep in mind when one looks at data quality, I like to stress that quite often the data set being analyzed went through a lot of transformations, and I may be 4 times removed from the actual data. If I have raw tables, for example, from Epic EHR, it may be more than, and it can be thousands of tables. On level 2, I may boil it down to fewer tables for my internal institutional needs. I may restrict it further to some subsets of population of interest, and maybe at what I call a data sharing level, or integrating data across multiple sites in a schema such as virtual data warehouse or OMOP. But it's far removed from the original native EHR data. So as I said, the goal was to design something like so intuitive as Glasgow Coma Scale or APGAR score, or reviews for a data set and some sort of quality ratings. Another problem was, for example, APGAR score puts the same weight on color of the skin as maybe the sound the baby makes. So it's difficult to make value judgments whether 10 years of medication history is equally valued as 10 years of height and weight history. And if one doesn't want to make those trade-offs and value judgments, the best way is to go with basic patient counts. So this was the vision I had back in 2010, almost 6 years ago, that one would look at a series of measures, and with something which doesn't put any value on particular subset of data, one could see objectively which institution shines and which one is less suitable for a given study. And this is where those measures are better explained, like count of all events. So I have 500 million events But if I have the same number of events, but in one data set I have 1.7 million patients, and in another data set 0.3 million patients, I probably have a higher granularity. And this is actual results. So that previous slide was a vision, but this was a comparison of data set at Marshfield Clinic with a data set at NIH, the Beatrice database of intramural research subjects. And there are the measures such as count of patients which have at least one prescription, or one prescription plus diagnosis plus lab result. And the data set may quickly drop down to smaller numbers. And that old work, now it's the Google code now is in the archive mode, but one can still, this was really a precursor to the study, as I said, those mini studies 1, 2, and 3. The final mini study where I realized that vision on putting next to side by side not 2 data sets, but I managed to put 17 data sets, and whereas the original 2012 study used either I2B2 or some other native schemas, with common data models such as the OMOP or Odyssey Common Data Model version 5, it really enables authoring code which runs on multiple institutions and multiple data sets. So I was able to compare 17, and one has to come up with a Greek type of name. So the name Iris stands for a goddess of the rainbow. And it doesn't have a meaning in terms of acronym. It's just selected as a, finally go with the female name rather than an all-male name. And so this is back to the comparison of the 17 results, and I blacked out those who are in, which are in billions count of events. All these counts are in thousands. So I can see immediately that, and the data sets are masked. So data set number 3, in terms of number of patients, it has 11,000 would mean it has 11 million patients, 11,000 thousands. And then it doesn't reduce much if I require some quality criteria. Whereas here I may start with the data set number 14. I hope maybe my mouse is being projected. If not, I'm looking at data set 14. A data set of size of 141 million patients may shrink to basically 5.9 million if I require certain quality criteria. But common data model allows to put lots of data sets and compare them side by side. And as we progress with big data in healthcare, there is increasingly choice in terms of which data set we will run the study on. So this was those precursor studies, the mini studies which led me back in a long time ago, I would say almost 6 years ago, some of them. In 2015, the core of this presentation, I embarked on a study which compare output of one data quality tool. And this is the study pending publication. It's in the review stage, so I will be brief in terms of some of the aspects of the study, not to violate the policy of not presenting elsewhere prior publication. But the study was titled as Multi-Site Evaluation of a Data Quality Tool for Patient-Level Clinical Data Sets. We did not have 17 data sets. We had, in fact, even more. We had 24 large healthcare data sets. Some of them were the same as other institutions, undergoing a little different extract, transfer, load, ETL transformation across 7 different organizations. And the goal, again, the common data model allows creation of a data quality tool, and I was greatly inspired by the fact that Odyssey community had such a tool, even in their precursor called OSCAR. It goes back even more than Odyssey, creation of Odyssey or OMOP. And the tool is called Achilles Heel, or Achilles for data characterization, and the data quality component is called Achilles Heel. And in addition to comparing output from that tool, we had a part of the study which asked structured emailed interview questions about the context in which Achilles heel or other data quality checks are being executed at a given site, at all those 7 sites. And this was really a brief, sorry, I'll present the questions we asked. In terms of that study and the manuscript we wrote, we introduced some conventions that we refer to the source data from EHR as source, and if they are converted to common data model, for example, version 5, we call these a target, conversion from source data to target data. And the goal is really to find errors in the data, if it's all about data quality. And some source data errors are inevitable. If there is a typo in gender or typo in height or date of birth, these data errors typically don't have a pattern, although they may. It depends if it's a systematic issue with an EHR. But they may or may not have a pattern. Whereas the second type of error, ETL, extract, transfer, load error, the things we do to the data to convert them from source to target. If there is a problem with the SQL or other code which does that conversion, transformation, that would be an ETL data error. And hopefully we would be able to find those ETL data errors through some systematic checks. And a special case is a mapping error if the ETL error. And what is influential for that manuscript or that study was a publication by Michael Kahn and colleagues, transparent reporting on data quality in the eGEMS journal. And there's a website of a group which tries to advance that field. And I'm a member of that group, and I'm very supportive of these efforts. And I like what they set out as a framework. And this paper lays it down nicely. This is actually excerpt from that Michael Kahn's article, where data quality problems are sectioned into 4 domains. How do you capture the data? And there are 6 recommendations or 6 points to publish once you publish a study which is using a given data set or data repository or database. The second domain is what you have done to the data in terms of data processing. Describe that, such as how did you map from source to target values, codes. The third domain would be characterizing the individual measures which appear in the data in terms of count, ranges, percentage of missing, and things like that. And this is where Achilles heel or an Achilles is mostly positioned. And the fourth domain is study specific. So this would mostly span the 1, 2, and 3 because it's difficult to design study specific ones on a generic level. I hope actually many of you would be familiar with in the IMEDS research lab. If you are, I'm expecting many of you might be using that as well. So if you go to a section where Achilles is available, one can, from the drop-down of reports, select the Achilles heel report, and this is where what we analyzed essentially in that study. If you click export to CSV, or if you export it through a SQL query, you end up analyzing this data across 24 data sets, and which data quality checks trigger the most, and things like that. These were the 5 data quality questions we asked to the 7 sites, such as when did you execute Achilles heel? Our goal was to get Achilles heel outputs after the first transformation, right? The first initial rendering of the common data model data, not after maybe a year of improving it or iterations. At some sites we were not able to achieve that, and we communicated when it was not the case. The second question was, what was the impact of seeing the results on your ETL or next steps? How frequently do you update the data or perform data quality tasks, and what resources do you have available for that? Besides Achilles heel, are there other tools that you utilize for data quality? And final questions asking about documentation. But this was not a comprehensive qualitative study. This was rather an add-on to the main study of comparing the output of Achilles Heel, the data quality tool, on 24 data sets. I also need to present some background of how Achilles Heel works. And if you're familiar with that, you can just skip for the next few slides. The Achilles works in 2 major steps and then a display on the website called Achilles Web. And the paradigm is to go from billions of rows of data on patient level to what I would say to something smaller, let's say 2 million rows. And that something smaller is a result of pre-computations, hundreds of measures. I think it's 148 measures, little pre-computed numbers. Either they output 1 row or 10 rows, or sometimes they may output, if they are highly stratified, they may output maybe 2,000 rows. But the idea is to pre-compute certain views of the data and measures, and then in the second step use those pre-computations and to do the data quality rules or data quality checks on these pre-computations. If you are fond of SQL like I am, this is just a view under the hood that if you do those data quality checks, they all live in an SQL file called Achilles Heel. And for example, I have a running example where I have this rule 26, and I'm basically checking whether quantity of a given drug, drug concept ID, is over 600 pills. And if it is, it's flagged as an unusual, as a warning, as an unusual value. And it operates on this analysis, pre-computed analysis number 717, and this is the actual rule. If you want to understand where the 717, what exactly it computes and how it came to be, you go to a second SQL file, not Achilles Heel, but just Achilles. And the analysis 717 indeed is operating on the drug exposure table and looking at the drug concept IDs and the quantity as something it analyzes. If you are not fond of SQL, then, which I don't blame you, you can go to just an overview of all analyses of all rules. So if I look at what are all the different rules out there, I can see, in fact, there is more than 28 rules. Some of the rules are what I call umbrella rules. They perform multiple checks on multiple pre-computed analyses. But the running rule I have as a running example in this presentation is the rule 26, and you don't have to study the SQL to basically say it's going after implausible quantity for drug, and if it's over than 600, then the type of error is a warning. It's not a error is a true error, which is very significant. Warning is something considered less significant. And in the newest evolution of Achilles, we are considering also something called notification, which would be even weaker than a warning, but still something you may want to know. Similar as CSV file is for the pre-computed analysis. And if I would scroll down back to the running example, and I mentioned they are stratified. Some of them, for example, this one is not number of persons. It's 1 row, and it just outputs how many people there are in the data set. But others are highly stratified by calendar year, by gender, and age. So that running example worked with analysis 717, and this is stratified by drug concept ID, and it's looking at quantity of drug by drug concept ID. So this was the end of that short introduction to what Achilles Heel or Achilles and Achilles Heel does. In the study of 24 data sets, this was the overview of the 7 sites we used and the type of data they had. And we try to mask what sites is what, and masks either the results so people don't have to be worried that their data quality issues would be too exposed. Another result in that study of comparing the Achilles heel output out of 24 data sets was how many errors each data set had in Achilles heel. We provide the context whether it was after initial ETL or after multiple ETL, so that is important in comparing data set to another data set, and roughly the classification of how big is the data set. We actually excluded site A from this overview for a number of reasons. Another table we present in that study, I was describing that we were trying to compare how common are different data quality problems, or which rules fire most often at the different data sets. So this is ordered in a descending order by within how many data sets a given error or a given problem was detected, and those errors which were detected at more than 10 data sets, we basically present those 15 rules or 15 data quality checks in that overview table. Some of them are related all to the same underlying problem with possibly incorrect date of birth. And so this was another result in the and some rules operate on a principle that they always have the same number of instances as there is data sets. It's basically going to output one error row. But in others, if it's structured by drug concept ID, I may see that 12 data sets had the problem, and if I tally and count in one bin all the different errors, I see that there is 3,000 instances of this problem within different concept IDs, but it only appears at 12 data set, not in all 24. So then, short conclusion of the first study, and these are only for the purposes of the priming for the next part of the talk, not all the conclusions we found. I have not presented, for example, the results of the data quality survey of how the different sites use it for the reasons that it's not fully published yet. We like that this was the first publication which showcases that it is possible to create a data quality tool thanks to a common data model, which if a site has not done any data quality checks or has delegated this problem to the principal investigator of any user of the data, it is possible to write one, and it is possible to extend with new rules, with new checks, with new measures. We have done that survey, as I said, which was a huge inspiration for how this tool can be improved or what matters to people as they are using the tool. I presented that which rules were important, those top 15 rules which fired at more than 10 sites or 10 data sets. And how do you compare quality? We actually were not able to, with that overview of different errors, we were not able to compare how deep is the error on how many drugs. Well, maybe with some sub-analysis in some of them we could have. But we had to improve the Achilles heel output to be able to better compare the depth of the problem. So we only knew that the problem is present, but not how deep. And again, the main purpose of that comparison study was to contribute to Achilles heel. That's where my later work comes into force, where in that prior study, in the study one, I only used something which the Odyssey community, mostly the team from Johnson & Johnson, wrote. So this was kind of an introduction how to contribute to that tool and how to extend the rule set. So concluding the description of the study one and comparison of outputs, I want to present one slide about that data quality collaborative, which I already mentioned. This is a group, all the details could be found at this website of Data Quality Collaborative. They meet regularly, mostly with an informatics focus, informatics researchers rather than health services researchers focused on a given problem. There was the core enabler was a grant from Patient-Centered Outcomes Research Institute focused on data quality, which I believe is almost at the final stages now. And what that group also tried to, in addition to publishing lots of, or a few articles, several articles on the subject of data quality, they also published a way to share the output of pre-computed analysis, something they refer to as data quality common data model. So it's not meant for representing patient-level data, but for output of data quality computations or efforts. Unfortunately, I was using the Achilles terminology for pre-computed views, as I was calling them analyses, and on the checks on these pre-computed views as a rule. In that group, they refer to the analysis as measure, and they refer to what Achilles would call a rule. They refer to as a data quality check. So the terminology is slightly different. Measure is analysis and check is rule, but it's easy to convert. And that is an interesting group to watch and collaborate. In fact, the extensions of what I'm going to talk next in that study too, I'm trying to make the additions which we try to add to Achilles consider how they could be added if people are using some other common data model, not AMOP/Odyssey version 5, for example, but Healthcare Systems Research Network Virtual Data Warehouse, or PCORE-NET, or Mini-Sentinel or Sentinel. So how could we write more generalizable data quality checks? So in that second study, which is ongoing, and we have only limited results. Mostly, it's easy to get results on the IMEDS dataset in the research lab. So that already creates a nice crowd of, unfortunately in version 5 only 3 datasets, but that's good. But ideally we would use it on more sites than just a Reagan-Udall Foundation IMEDS program. The extending Achilles, we have introduced some extensions which were incorporated in early 2016 based on the quick implementations of the problems we found in the study 1. We introduced that rule ID, which I already presented, but it wasn't there at the time of we were running the study, and the rule overview CSV file. And we improved that how many offending rows, it's now separated out in a separate column in the output table called Achilles Heel results. So it's gonna, if we ever do that study again, it'll be much easier. We won't have to do any regular expressions to try to extract something which was not well put into an unstructured field. And in the kind of emerging version 1.3 of Achilles and Achilles Heel, which some of the improvements are already in the master branch. So if you would be installing it from GitHub in R, there's a way to install the most current and recent version of any given package. You would already get some of those measures. And in that new version, we introduced the concept of derived measures. If there is something already pre-computed and we need a different view of that problem, for example, there may be stratification of death by year and death type. If we just need to see how many death types, whether we see any death in hospitals or death received through Social Security index or through the local health department, so that would be a derived measure. The same for drug type or visit type. Many of them are highly stratified, and if we need a slightly different view, this would be derived measures or derived analysis. And if someone is using other common data model than Odyssey or AMOP, they can basically jump quickly to just write their custom code which arrives at those measures and still reuse the same data quality checks. And Another goal we have is we want to compare some common characteristics of the data. For example, an average 50-year-old, how many lab results we should expect in a data set, which is, we use something called a utopian data quality assumptions, where we set a very high bar for what type of data we would like to see. We expect basically a lifetime EHR record with patient-entered data, with data from health claims from health plan, extended with data from electronic health record, including numerical lab results. So the idea is to put a relatively high bar, and many of the data sets would not be, almost none of the data sets currently in use would meet that high bar, but at least it would expose it. What are the issues found in the data sets, given that high bar or high expectation? In that effort, the Data Quality Collaborative had a number of initiatives to classify things, to name things. So here I am with yet another classification of data quality pre-computations and checks on those pre-computations. And I like to always say that one is by purpose, that I may have many of the data of Achilles pre-computations are not data quality. They are meant to characterizations that view the website where we can see data density and tree or table view of drug exposure table or procedure table. These are general purpose measures, such as percentage of males or others. If there is a measure which is specific to data quality, it may say invalid X or invalid provider ID or other things which are not good for general data characterization. They are only good for data quality. The next classification is whether the output of the measure is single row, such as count of providers, or I should expect multiple rows. And if it's a simple type, like a death type or drug type, visit type, or provider specialty, it may be less than 100 rows or medium output. And if I stratify the measure by calendar month and age decile, I may end up with thousands of rows. But the measures could be classified whether the output a single count or multiple structure, which is somehow has to be analyzed using that structure. And finally, or most importantly for this portability of data quality checks, is whether the rule or the measure has either a terminology dependency built in or a model dependency built in. So if I have a rule which checks for unusual procedures given gender, for example, hysterectomies seen in males, if my common data model is really using SNOMED as the main diagnostic measure, the measure will already have a built-in dependency on terminology, and I would have to create a data quality specific measure where I would abstract out those hysterectomies in the definition of the measure to be able to perform a generic data quality check on that. Another dependency is the dependency on the model. So if I check that I expect at least one numerical lab results per 1,000 person sample, if it's a high quality data set with lab results, it is dependent on the notion of what do you consider a lab result, where do you look for lab results in the measure table, for example, in version 5. So this measure would have a model built in, whereas they all would have a model built in to a degree, but to a lesser extent. So for example, I can just say, I don't expect any events prior birth or after death, or after prior conception and after death, and that has less model built in. It's a very generic rule. And to also comment on some of the, hopefully doing okay on time, 42 minutes into the presentation. I haven't presented much of the Cloud Lab related stuff, but to briefly address that. So currently in the research lab, if you are also users of that lab, you see the Heel output and pre-computations done on the Common Data Model version 4. before the fall 2015 data refresh, which I'm very grateful for being done by the IMEDS team. So in 2016, there is now version 5, and within our group, we have internally obviously executed the Achilles Heel on those new version 5 data sets. They are simply not exposed within the research lab, including some of the new derived measures and exploratory measures or pending measures which we are working on yet, for which we, for example, are determining thresholds. And I think this is my conclusion slide. I have one other optional slide. So I mentioned prior studies which led me to this problem. I mentioned this main study, 7 sites comparing outputs and additions. And again, I want to stress that this is really an informatics type of research, not a clinical. And with that, I'll be happy to answer any questions.
Wonderful. Again, thank you very much, Dr. Huser, for presenting to us today. So for the remaining of the time we have on this call, I'd just like to open up the call now for a question and answer period. So I'll now be unmuting everyone. So if you'd like to speak, please announce yourself and feel free to do so.
The conference has been unmuted.
Great. Anyone has any questions?
Hi, this is Alec Walker. Vojtech, could you give us more examples of the analyses that later get tabulated? You showed us age out of range, and I think there's thousands of different kinds of things that you look at. Could you kind of help us understand a little bit more of these small analyses that are done that are later tabulated?
Yeah, it's maybe that's when I try to opt for the interactive part. Probably the best way to address this question, hopefully you are able to see me browsing GitHub. I can show you lots of CSV files, but let me show you a best way to get to it probably and try to address that question. So if I, within the Odyssey OHDSI GitHub account, if I go to Achilles, and they live in multiple places. They live in the SQL code, but for the benefit of those who don't want to dig into the code, one can see it in the CSV overview. So I would refer you back to that overview of all those analyses. In fact, I would have to switch to raw view. They sometimes skip numbers, as you notice. They go to 420 something, and then they suddenly skip to 500. Let me try to make it larger. So it's not 1,800 of them. If I scroll now to the bottom of it, in fact, there are now in the dev branch, there are some in the range of 2,000 and 1,900. But there is about 199 of them. There used to be 198. I added those even to the master branch. So that's the best way. And the next best way, but these are not very well described. What is helpful is this stratification to the right. I can see how they are stratified. If I see a rich stratification, this will be one of those measures which outputs thousands of rows rather than just 1 row or 10 rows. And it's actually even some of them which says what it says distribution, they would live in a separate table. There is a table for just counts, and then there is a table which has more richer structure. And that is a problem for moving the data to the data quality common data model. But if hopefully that addresses a little bit your question, that is the best way. And going to the SQL file, although some of the SQL code for some of them is 3 or 4 pages long, and it is not that easy. And there are very few comments in the code, or there are no comments. I try to now comment some of my new analyses and new codes, new rules which I'm doing. And the same goes for rules. If I would, let me leave it at that. Any more things I should add to the answer?
No, that's very helpful. Thank you.
Great. Anyone else?
Yeah, this is Hugh Kawabata from Bristol Myers Squibb. Thank you, Dr. Huser. This is wonderful material, kind of a systematic way of looking at data quality issues across all these databases. The one question I have is with regard to some of these quality issues that you've identified. Are there any activities that's taking place to address some of these issues? You know, the one I'm thinking about here is your drug dosing that's over 600 pills, for example.
So that is a huge debate. We, unfortunately, in our mini survey, the key question to ask is saying, what do you do with the error rows? Do you just delete the error row and leave the rest of the patient there? Or do you try to suppress the whole patient, which might have a typo in the birth year or in gender? What do you do with the what I would say either the problematic rows, events, or problematic patients? And if you have more than 100 million patients, and you would be removing less than 0.00001%, you are probably not introducing any bias into the data set by simply removing the whole patient from the data set. If I see any issue on that patient, well, I will lose 0.0001%, but I won't be embarrassed when I'm presenting my results. And I think that is the case with the typos in the source data. I mean, typos will always be there, and it's a legitimate strategy to basically eliminate the ones where there are typos. You are still left with plenty of patients to analyze and hopefully not introducing bias again. So we have not asked that question what the sites typically do. But I wouldn't, the fact that I am now seeing in the IMEDS, and the same are all of us are users of the research lab, so did we document what is done? Because actually on the version 4, there were lots of errors found by the Achilles Heel, and some of them were addressed in subsequent ETLs. In the new ETL for version 5, we are not seeing that many, and there is no way to tell why are we seeing less. Is it because I can actually suppress maybe 100 error patients and make it look like a much fancier data set. Or it depends how I look at all the checks. If I really, we also try to make some of the checks relative. So we only say, well, we see 3 million funny drug rows, but in the total amount of 5 billion, it is not something which you should be, maybe totally concerned about. And maybe if it's never in your study drug, then it's still safe to pursue. So I think some errors should be, basically the whole patient should be suppressed. Other errors should be maybe the event may be suppressed or ignored. Maybe a most cleanest approach is to leave all the errors there and basically let the user know that they are there.
I'm inclined for that solution. But one thing, even though these errors may represent a very small proportion of the entire database, in a particular study, it may affect your results by a lot, because the errors are not necessarily distributed evenly across the database, right? Anyway, thank you.
Yeah, I agree that the safest approach to leave them there. Although if someone who is trying to license data to a drug company, I wouldn't be surprised if they really just remove a few patients to make it look nicer. So it really depends on the perspective of the curator of the data.
Hi, this is Bin Kai from Pfizer. Thank you very much for the excellent presentation. And my question is, do you have or plan to do some analysis regarding the association of Achilles heel measurements with the validity of epidemiology analysis, or which dimension or which measure of the Achilles heel score is more important to the validity of epidemiology analysis?
So Achilles heel currently, if I understood the question correctly, it is, first of all, it is not geared, it's on the data set level. So if you are conducting a study in, for example, osteoporosis, it's not trying to check, okay, well, for osteoporosis, you will need, for example, bone mineral density reports and Z-score and T-scores as results, lab results or observations. So it is trying to stay on a data set level. So it will never be able to do those study-specific checks. And even in terms of those generic checks, it still has a huge room to grow. I know, for example, that the mini-sentinel data quality checks, which are mostly exposed within the network, within the site, they're not publicly, or if one asks nicely, they might be available, but they have maybe hundreds or thousands of checks which go after the actual ranges of, let's say, LDL cholesterol values or other laboratory results, and try to mark the outliers there as well. So currently it is not, but I would say if I go back to the overview of the analyses, it would, some of the analysis 406 or 606 and so on is, or 405, this one, number of condition records by concept, condition type, or actually no, this one is the 404, and then similarly 604 and 1804 for measures. These are the best measures to expose. And I have, for example, also looked at those if it's a pediatric analysis, and in the development branch of Achilles heel there is now this terminology-specific rule. The example is we are seeing meconium, diagnosis of passage of meconium, which is this first stool in your life, and we are seeing 50-year-old males being diagnosed with passing meconium. So this is where we drill down. We just pick out the 2 or 3 concepts and try to go by very focused data quality question. One could also try to design all these things in a generic fashion, try to design some statistical principle or generic principle of either generically go by date of birth problem, or generically go by date of death problem, or generically go by age, or no, that's actually that, by gender, and statistically try to see all the pointers which might indicate a typo in the, or error. So they're not very sophisticated at this moment, and definitely not at the study level.
Thank you. This is very helpful.
And if I still can, there is still 4 minutes of time. I had one extra slide, and maybe I'll present it. The extra slide is, in addition to say thanks to the IMEDS infrastructure and to the IMEDS team, I want to mention maybe like a wish list or limitations. And if I would wish only once, I would probably opt for trying to get all data sets in the version 4 or in the version 5. But some of the others, I'm a researcher who has actually a writable schema in the Redshift infrastructure, and but some of the Odyssey web API and some of the most advanced tools, they require one writable schema per data set. So that would be kind of on my another item on my wish list. So to fully implement the Odyssey web API and the infrastructure, which is saying, well, if I have a GE data set, I have to have a GE results schema where all the pre-computations will be able to live and persist. and I can reuse them later. And this would also enable all the cohort-based tools and global cohort infrastructure and the CERSI tool. Currently, I know IMEDS has a tool developed internally as well for cohort selection, but it's especially with the newest recent deployment of the new version of Atlas, it would not be that tedious to be able to deploy CERSI. But so back to your questions, if there are still some.
Great. So I guess if there are no more questions, so I just want to say again, Dr. Huser, thank you very much for presenting, and thank you also for your input on the lab. And also thank you for everyone for joining and participating on our call today. So our next community call will be on Friday, June 17th, and you will be receiving an email from us with the topic of that discussion soon. Again, so thank you all. Thank you, Dr. Huser, and hope you all have a good rest of the day.
Okay, thanks. Goodbye.
Thank you.
Thank you.